So I'm going to talk about neural combinatorial optimization using reinforcement learning, and one application of it will be device placement. I'll describe what I mean by that. I want to mention the fact that this is work done with many people, and in particular the first three authors, Azalia, Erwan, and Hugh, were brain residents with us for the past year. So when they started a year ago, they didn't know anything about deep learning, and they learned with us, and they were quite successful. So I think it's great to see that. The other ones are normal Googlers. Okay, so the content of these talks are available in these two archive documents, if you're interested. So okay, let's see. I want to talk about neural combinatorial optimization. So combinatorial optimization is a problem that we have to solve every day. There's plenty of actual problems that are underlying this, like the traveling salesman problem, packing, scheduling, manufacturing. There's a lot of problems that at some point need to solve some combinatorial optimization problem, and what we usually do is we design, because they are often NP-complete and hard to solve, we actually design heuristic to try to solve them. For each of these problems, we try to find the best heuristic, and it takes a lot of time, it's tedious. So the question is, can we actually automate all of that and have just a deep learning box that would solve it for us without in the same way that we've been doing for all these other deep learning successes, where you don't have to design features, you just put your model in the black box, and suddenly the solution appears. We know it worked for a few other applications recently, so why not combinatorial optimization? So in fact, about 2 years ago, a colleague of mine, Oriol and his colleagues, proposed this model called the pointer network. And they actually applied it to combinatorial optimization. So the way they applied it was the following. They would take the combinatorial, the problem to solve, say the TSP, the traveling salesman problem. They would encode it using an encoder, and I'll explain how we can do that. And then they would have access to a training set of traveling salesman problem for which they had access to the actual solution, the optimal solution, and they would just try to maximize the probability of generating the correct solution given the representation of the model. And that actually worked quite well. You should read the paper. What they would do, so they would maximize the likelihood of getting the right solution, and then at inference, they would just try to find the maximum a posteriori solution, and that would be their solution. Now, the problem, obviously, is that these problems are hard. So if you need a training set of many of these problems to solve the next problem, it's going to take a while to get them, or you're only going to solve small problems. So supervised learning actually has its limit at this point. We need to have the problems to be able to solve them. So I think that's a limit that they couldn't go around. So in fact, what we propose here is just to change a simple thing, which is using reinforcement learning. So what we're going to do now is we're going to generate, say, traveling salesman tours, random ones, and we are just going to try to compute the cost of a given tour, and we are going to use reinforcement learning to minimize that cost. So now we don't need to train with the optimal tour. We can train with any tour that the current model finds, and any of these tours will give us some information that we can use to improve on the next tour and the next problem. Sure. So we're not going to solve all of them, but there's a lot that we can do solve, and we're going to talk about that. Yes, I agree. So I think the main intuition here is that reinforcement learning gives us the opportunity to use information even if we don't have the final optimal solution. Any tour gives us some information about our current model, and we can improve on that by gradient descent. So we need a way to parameterize a problem, and indeed we're going to use the sequence-to-sequence model that we've already heard a few times in the past talks this week. So what we use is a recurrent net where the encoder is, is that supposed to, like this? Yes. So this is the encoder, and we're going to have to serialize our problem. So if if we're talking about the TSP, we need a way to serialize cities and their locations. We're going to put that into a recurrent net, and then we are going to output an order in that case, which will be, so we're, for the TSP, we're actually going to use the famous pointer network. A pointer network is just a sequence-to-sequence model that has the particularity that the output here are just pointers on the input. And that fits well the TSP, because what we want is to indeed output an ordering of these inputs, the input being the cities in that case. So not all combinatorial optimization problems can be expressed like that. Some of them will be expressed by a pointer network. Others will be expressed by some information you have to output, whether it's the number, I don't know, the number of objects you need to put in a bag, or it could be other things. We're going to see examples for the device placement later. Doesn't matter. You need to have a way to represent the solution in a way, and I guess a recurrent net can represent any of these solutions. So how do we decode? Well, there's nothing special here. We're going to parameterize the solution as a probability distribution over solutions, and if the solution has multiple parts like cities, then the joint probability of all the ordered city will just be the probability of one of the city given the previous ones, which means we've encoded the cities here, for instance, and now we are going to decode them one at a time and provide as input the previous decoded cities that that our model has found. So any single part of the solution will be conditioned on the previous part, as well as the problem. And once we've solved all that, we have the likelihood of the solution, the complete likelihood of the solution. So how do we train this? Again, there's not much difficult things here. What we want using reinforcement learning is to minimize the expected cost of the solution that we're going to get with our model. So that's what this thing says. So we have the problem. We get the solution with our encoder-decoder model. We can compute the cost. That should be easy. That's most of the combinatorial optimization problem have this characteristic. Not all of them, but most have this characteristic that it might be very difficult to find the optimal one, but it's usually very efficient to compute the cost of a solution. So this doesn't cost you that much. And what we want is to minimize the expected cost. And since the solution is usually expressed by a sequence of decisions, like take this city or give turn left, whatever, it depends how you encode the solution. You cannot use directly gradient descent. You need the trick, and we use the reinforced trick. Reinforced is this trick that dates back already now a few years, which helps us compute the gradient through this cost here by basically rewriting all that. Just basically says that in order to minimize this, you can just weight by the cost the gradient of the log of the probability of the solution, and if you do this, you are going to actually minimize the cost of the next solution. So that's great. The problem is that this gradient has a lot of variance, because most of the times, the cost will be like infinite or very large, and so it can be very slow to train. So we use, in some of the cases, we use a more recent algorithm called actor critic, where we have another, so this basically, the only thing to notice here is this line where instead of weighting by the actual cost, which here is the loss, that's how we call it, we subtract a bias that is also estimated, and it's actually an estimate of how the cost will be. By this simple trick, and B can be computed in various ways. Here we actually use a neural net, but it can be anything you want. Using this simple trick reduces the variance of the gradient that you get, and so it actually just trains faster. It's not needed, but if you do it, you're going to get faster results. There are many tricks that you can use, and that's the one we use in some of the experiments here. So you can train basically as long as you want, because when you train, you generate problems. Say, for instance, you generate TSP sets of cities, and then you generate a solution. So you generate a problem. You can generate as many as you want. Then you generate a solution. Then you just try to optimize your loss. Now, what do you do at Inference? Well, at Inference, you have a series of options. The first one is you'd like to have the actual maximum that you would get. Of course, this one is impossible to get. It's NP hard to get. So instead, what you could do is the simplest would be greedy decoding. So you just look at the max of the first city, you take it, then you put it as input as the next input to compute the next city, and you look at the max, and you go on, and you get the greedy solution. That's good, but maybe you can do better. You can do a beam search. So instead of just looking at the max, you can look at the K max, actually the B max here, and maintain a set of B partial solutions while you decode, and continue on until you finish and you take the best of the B solutions that you found. This trick is used in many sequential applications like speech, machine translation, and all these things, so there's nothing new here. It doesn't cost that much. It's just B times to maintain. Another solution is to sample. So you have a full probability distribution over your cities, so you can sample. There's no problem. But there's something even more interesting. You can do what we call active search. You can actually, you can continue training on your problem. So let's say you've trained a deep network, a recurrent net to solve TSP problems. That's fine. Now you have one TSP problem to solve. Well, this single problem, you can easily overfit your model to make it better. So you sample one, you can compute the cost. It's just the sum of the two or length. And now you can compute the gradient on it, modify your model, and sample another one, compute the gradient, modify your model, compute, and do that as many times as you want. So it's not that you're just sampling. You're sampling, and then you're improving your model. The more you do it, the better you are on the actual tour you want to optimize. So that the barrier between train and test becomes murky at that point, because you're actually training on your test example, but you don't care. You just want to solve that problem. So some result on these like toy TSP problems. So let's see what I should say. So this number here, 20, 50, and 100, are the number of cities. So it's very small. So these were, we took these numbers because we wanted to compare to this paper, the pointer network, which used a supervised learning set of known tour for which we had the solution. The numbers that we see in this table are the actual size of the tour, so the smaller the better. These are the various ways you can decode. So you train, that's what we call here RL pre-training. You train on as many tours as you want, because it's random. You can generate as many as you want. And then you greedy decode, or you take the top 16 here, the kind of beam search, or you sample, or you do active search, so you actually modify your model for this particular tour. And here you only do active search. You don't even pre-train on anything. You just try to solve this particular problem. And now after that, there are other baselines. So Christophides is a known baseline that is guaranteed to be at most like twice the size, I think. This is a toolbox we have at Google that has most of the known algorithms for all these operations research or combinatorial optimization problem. And this is the optimal. The optimal can actually be solved for this small tour because people have actually built solvers that are specifically good for TSP. So it's hard to beat, of course, and they get to the optimal. And our goal was not to beat them, obviously, because they were actually built for this particular problem. What we want is a generic tool that would take another problem and being able to solve it as well. So to summarize what we see here, well, we're obviously better than supervised learning. That was expected. We are not too far from the optimal, and we're usually better than most of the other ones. Now, active search is actually quite good. Only doing active search is not the best, so there's something to be learned by training on other tours, and then by specializing on the actual tour you want to optimize. So that's what these numbers show, and that's the best numbers. In terms of how long does it take to decode after you've trained, it's faster than the optimal ones, so that's good. But it's still getting slow as this number grow faster. So I don't think we've actually solved enough yet. But still, it's faster than the best models we know. Let's see. I'm going to. What this is supposed to show is the distribution of how good you are over like a set of I don't know 1,000 tours that we randomly generated. So that line is the optimal, and this is the distribution of the cost. So you want the distribution to be as near as the optimal. This is the ratio of the cost divided by the optimal. So if you always get the best solution, then you are exactly at that line. So the red line says that like 75% of the tours are actually solved optimally, and then it starts to degrade until it reaches, but not too far, like 1% degradation compared to the actual tour. So it's not too bad. One thing we wanted was to show that you can take the same approach and not do any tuning on anything and just change the problem itself. So now here we just tried it on Knapsack, which is another combinatorial optimization problem, and we just trained the same model, generated Knapsack problems randomly, and got, actually, in that case, we actually got the optimal. So I suppose Knapsack is easier than TSP. But I mean, the point was not necessarily to get to the optimal, but to show that you actually easily can get to any of these combinatorial optimization problems that satisfy some of our constraints, and easily get reasonable result. So that's good, but these are like toy problems in at least for the combinatorial optimization people. So even if in our community it's fun to work on that, for them it's clearly just toy problems. So we wanted to play with a bigger problem, and in particular we wanted to play with a bigger problem that affects us, and that's training large deep learning models. So you can train your deep learning model on one machine if that's the only thing you have, but if you're a big company, you usually have access to more than one machine. So the question is, how do you use these machines? It's not that obvious to use all these machines, and there are multiple choices you need to make. So can we actually automate that again? So let's take, for instance, a seek-to-seek model. So that's your seek-to-seek model. This is the input. Here it's used for translation. So you want to translate ABCD into ABCD. Well, it was just for fun. So these models usually have encoder that are usually like an LSTM or any of these recurrent net. Could have multiple layers. Could have attention layer, and it could have multiple output layers as well. And at some point you have a softmax. You can put all of that on a single machine, but if it's big, you may have problems. So you could decide to put it on multiple machines. Here I give an example that is very simple. You put all the first layer on GPU 1, your first GPU. The second layer on GPU 2, etc., etc. so that you can, in parallel, compute things here while you compute things here, and then all this can go like this, much faster than if you only use one GPU. That's one way you could do it. That's actually the default way I think we use in TensorFlow for many of our models. But is that the optimal? Not so clear. So can we actually find better? And I think that was the actual goal of the project. So what we basically do is we're going to generate a placement. So for us, a placement will be, so recap, we use a library called TensorFlow that I'm sure you've heard of. It's a library that you can use to do deep learning, to train models, to generate models and train them. And that library is based on the fact that you generate a graph of operations that you are going to apply from the input to the output. And so that generates a big graph that says, each node says, well, these are the input and these are the output. And you feed some of the nodes of the graph. You propagate the information and you get the answer at the end. So the graph is actually usually includes also, if you want to train, you're going to get, the graph will include like a forward pass and then the backward pass to update, to compute gradient and update them all. So you can imagine that these graphs are huge, and we can try to see each of the nodes in the graph. We should try to find where they should be computed. A node could be computed on the CPU, on the GPU, on another CPU, on another GPU, or on a TPU if you're at Google. I mean, any machine you want. So, so that's the actual problem. So we are going to decide on one placement, like this node runs on this machine, this node runs on this machine, and we are going to take a mini batch of examples, do a forward pass on it, do a backward pass on it, compute how long it takes to do that, and that's our cost. And with the cost, we're going to update the placement and generate a new placement and go on like this. So we're going to train that by reinforcement learning exactly the same way I just described. And our cost is just how long does it take for this placement and this mini batch to get a forward-backward pass. So now we need to encode this placement, and the way we encode it is using a recurrent net, the same way. So we are going to have each of the node will be inputted in a serialized way here. So this is one node, it's inputted, another node, it's inputted. And then once we're at the output, we have an attention mechanism on the input. And we output on which device should run the first node. And then given the device that the first node is running, which device should run the second node and go on like that. So at the end of this, we know for each node which device should run it. So we wanted to try that on real problems, not just XOR, say. So we took 3 of our big models that are actually useful. One of them is Inception V3. That's a model that you can use to train ImageNet type of model. So these are like the best models we know for training an image recognizer over 1,000 classes. There's this ImageNet competition, and that's like a good model for that. Maybe not totally the state of the art, but very much near. RNNLM is a language model, a recurrent net that is trying to maximize the likelihood of a sequence of words. And NMT is our neural machine translation, which is similar to those that we actually use in production. So this is the size of the graph. So that's the number of ops in the graph that represents these 3 models. Now, these are big numbers. So for this experiment that I'm going to show you, what we did was group them into groups that we are going to be collocated. So for instance, we're going to collocate the gradient, so the forward and the backward pass of each node. We're going to collocate things in a convolution and stuff like that. So these are heuristics, and we're not very proud of having to do that, and actually we have a version that works without this, but for now, for this experiment, we have a heuristic that goes from this number of ops to this number of groups of ops. And we're only going to optimize the placement of groups of ops instead of ops. Okay, so these are the results that we get. So this is the number that we see here is the time to actually run a forward-backward pass. So the smaller the better. So these are the numbers if you run on CPU. This is the number that you get if you just ask TensorFlow itself to do a placement. These are if you have access to more resources. So if you have access to 2 or 4 GPU, for instance, these are heuristics that we can use to solve the problem, Scotch and MinCut. This is if you ask a human what should be the placement. Here's what they get. So this is what we get, and this is improvement of what we get over the best other ones. So what we can see is that for inception, we get about like 19% improvement over the best ones. For neural machine translation, like 20% as well. For RNNLM, we were not able to get better than what TensorFlow itself was providing. So, but at least for the other ones, we do get about 20%. So that's good, but what does it actually mean? So here is an example of a solution that is found by our procedure. So this is for the neural machine translation graph, which includes here like an embedding layer, the first LSTM layer, LSTM2. I mean, this you can see here roughly what is the model. The color coding is white means the CPU, and then each of the color mean a different GPU. So it's not at all the same thing as if you were to ask a human. It finds a very special way to encode and go from a CPU to a GPU to another GPU and etc. Something that a human would have never found. But this is 20% faster than if you were to try yourself. So similarly, this is a picture of the model for inception. So it looks like a big snake. And again, so this is, I guess, the input, and this is the output. And it goes like this. It's a big convolution net. And again, you see the color coding that is not that evident, but this is about 19% faster than if you were to decide yourself on a placement. So what this says is it seems that there are ways to improve if you ask a machine to try to optimize that a human would not have found otherwise. So I'm at the end of my talk. What I wanted to say was, sure, recurrent net can encode very complex problems. That's great. We can actually encode anything we want with them. We know that. Thanks to LSTM. Thanks, Seb. But reinforcement learning here is very useful because we can now optimize for things that are actually hard to optimize, in particular some of these combinatorial optimization problems. It seems to give good results on small problems, but it's not as good as a very specialized algorithm that you would have spent years on optimizing. That's clear. But when there's a new task, and I just took this task because this is something that we do every day, we have to train our models, and the combinatorial optimization did not spend 20 years on finding the best graph, so we had to find it ourselves, and when we try, we do better than the off-the-shelf solution that you would have if you don't have access to 20 years of combinatorial optimization experts. So with this, I'm done. And I was fast.
Yeah, well, we have about 15 minutes of
yes.
questions.
I optimized my speech while I was speaking.
Hey, Samy.
Yes.
Hey, Samy. You said that you used heuristics to go from operations to groups.
Yeah.
But you've also done some experiments where you didn't do that.
Yeah.
And worked on the operations themselves.
Oh,
Any
okay.
idea if the operations tend to get grouped automatically in ways that are similar to your heuristics?
I don't know, and the reason I don't know is that I have not participated in this further study. I know it works. I have not read the document that is written because I cannot, for some reasons. So I cannot answer. I just know that now we can actually train these models on like thousands of nodes without having. It's a hierarchical approach. So it decides first on a grouping, and then it decides on which node goes to which CPU inside a group.
I guess another way to ask the question would be, do you know if you get any additional speed up by not working on the group?
Yes, it does. It does. So these results that I showed you are now superseded by the new model, yes. So not only it's faster, but we didn't have to need a human to find it, yes.
Okay.
How big is the overhead of doing the optimization?
So the timing I'm giving you includes that. So it's worth doing. That's what I mean is that you can spend time on optimizing. If in the paper we actually give a result on how long it takes to train a model at the end, and since so the training time basically we include the time we took to find the right placement, and it's worth. If that's I think it's reasonable question to ask. Yes.
So the original pointer networks, they were kind of sensitive to in what order you
the order
give the
matter.
inputs.
Yeah, we wrote a paper on that.
Exactly. So is this different if you train with the reinforce?
I don't think we've done any experiment, so I wouldn't rule that out. It might actually be dependent on the order. So we took the obvious order of flattening the model from input to output, but might not be the right one. Yeah.
Can you go back to the actual performance numbers?
It's
this
one. Yes.
Yeah. So there's one thing I'm a bit confused,
Okay.
and maybe it's just how you present it.
Okay.
So if I look at number of GPUs, going from 2 to 4 GPUs doesn't really buy a lot. What's going on there?
Yeah, I don't know. Let's see. Actually, it's even worse when you ask a human expert. No. Yes, here. I don't know. It's a very good question.
Yeah, I mean, the reason I'm asking is because we actually haven't had the problem yet of having to partition inception-like networks of multiple GPUs. So that's why because you get trivial scaling if you just do the data parallel.
Oh, yeah, sure. We have that as well, but that's a different. That's a different orthogonal question. Right. Yes, of course. I mean, you get it for these small number of resources. You get trivial scale. You don't get it that trivial for hundreds of CPUs and GPUs. I'm sure. Yeah. But okay. Yes.
Any other questions?
But it's a good question, and I will get back to it.
Any other questions? Oh wow, that's quick. Then let's thank Samy again. That was pretty cool.
Have a break. Thank you.